All right, everyone, let's get started. So today I want to do two things. First, our topic of the day is retrieval-augmented language models. Before we get to that, I wanted to quickly review at least the first 4 quizzes and see if anyone had any questions. We will resolve those hopefully today. We'll go over the 5th quiz, the one that was due Friday, when we go over all the midterms next week. So, quiz number 1. I think this one was pretty straightforward. It was asking you to compare a count-based model, like an n-gram model, versus a neural language model. So the general idea here is that this prefix, chalkboards flap their wings, is very unlikely to occur in the text that these models were trained on, like Wikipedia, right? This sentence doesn't make any sense, but it's still a valid sentence in English, or prefix in English. You might imagine some imaginary scenario where there is a chalkboard with wings. And so this probably shouldn't get 0 probability, and things that follow this probably shouldn't get 0 probability either. The count-based model will give you 0 probability because this has never been seen before. This is an unsmoothed model, so there's no probability devoted to any unseen prefixes. The neural language model, because it's not treating these as counts, but rather as dense vectors, it has more flexibility in how to assign probability of these kinds of prefixes, and will give you something, at least, for this model, as opposed to either having no distribution or having, basically this prefix is never observed in Wikipedia. So that was the answer to this one. The second one, again, like we do this caching because it's more efficient. If we don't cache the partial derivatives during backprop, we're just going to have to recompute the same partial derivatives every time we want to compute the gradient for something that's deeper down in the network. So intuitively, this is a way to save space and time. All right, so let's just keep powering through these. Quiz 2 was talking about attention mechanisms, and here the first case was in an RNN, we have this bottleneck, right? So in a sequence-to-sequence network where we consider an encoder and decoder, and in the traditional setup that we described, the only connection between the two was the last hidden state of the encoder is used to initialize the first hidden state of the decoder. So all of the information about the input sequence has to be represented by the last hidden state of the encoder. Therefore, it forms this bottleneck, and attention mechanisms alleviate this by allowing the decoder to look at all of the positions, all of the representations in the encoder, not just the last one. So this is a way of explaining this bottleneck in the context of sequence-to-sequence models. But of course, if you're just using an RNN for classification and you put a classification layer on the final hidden state of your sentence, this is the same issue, right? You have a bottleneck in that you're forcing all the information about the sentence to be encoded in the very last representation. Okay, feel free to raise your hand if you have any questions, or I guess, okay. So the second question here was, how do we encode word order in a transformer-style self-attention model? This one was probably answerable in 2 words. You could just say position embeddings, right? We add these embeddings that represent the position to the input before we pass it through these transformer blocks. All right, so that's 2 of these. The third quiz, the first question was basically asking you what is the difference when you mask out 100% of or 99% of tokens versus 1%. So if you mask out 1% of the tokens in BERT, remember that the masked language modeling loss only gives you some signal over tokens that are masked. So if you have 512 tokens of input, only 1% of those are masked, you're not getting signal from the 99% of unmasked tokens. And as such, you need to see a lot more batches in order for the model to converge to a good point. So if you mask fewer tokens, training takes a longer time. It's more inefficient. However, there are pros to having just as few words masked as possible. And that's that for every mask token that you're predicting, you have almost the complete context, the complete surrounding context with which to predict the missing word. If I go to the other extreme and I mask out 99% of the words, sure, I have a lot of loss coming in from every single one of those masked positions, but I'm not going to be able to actually predict the identity of the masked token if I'm missing so much context, right? So those are the two main trade-offs. Yeah. So the Electra model doesn't have this issue because at every single position in Electra, we are getting some kind of loss. Because the task there is to predict at any position, is this a real word or a fake word? So it's a binary classification problem, but I get signal through the real words as well because they're real. So the classifier has to predict, yeah.
Is this a sort of question where like increasing the masking from 1% to 15% makes the problem a little bit harder, so there's actually less context, so the model can learn more from trying to solve a harder problem, or is that not accurate?
So the problem, sorry, I'm going to remember to restate these questions, although I already forgot in that case. The question is, going from 1% to 15%, doesn't this make the problem harder, but still not impossibly hard? Maybe this is desirable for the model. Possibly, but you have to remember at test time, you never see data with mask tokens. I mean, it depends on your task, but almost always you see a complete context. And so this harder task that you mentioned might not be relevant for, the task that you really care about is having as much context as possible for downstream applications. All right. So let's move on to the last one of these. So here, we asked you for 3 reasons why we might prefer character-based tokenization over word-based tokenization. So there are a couple of reasons, right? One that we talked about when we discussed, byte T5 is that if you have a multilingual model, then character-based tokenizations allow you to maybe apply same character or byte tokenizations, allow you to apply the same tokenization to a bunch of different languages, versus if you have a word level tokenization, then you're going to need to add all of the words in a new language to the vocabulary in order for your model to handle that. So your vocabulary can get really large. Another benefit of character level tokenization is the out of vocabulary word problem, right? So with a word level tokenization, I have to observe all of the words that my model is able to process or generate at training time. So if at test time I encounter a new word that wasn't in training, I have no way of modeling that. I have to convert it to an unknown token, and this is undesirable in many cases. Like if you're processing social media, for example, where a lot of new words are created every day. So character level tokenization doesn't have this issue, right? Because you imagine all characters, or all bytes, if you want to go all the way down, are represented in training, and you can form any sequence through a sequence of characters. So what's another reason? I'm just asking because I forget. Yes. Oh yeah, that's a good one. So the answer was with a word level tokenization, you need to keep separate parameters for every different form of a word, right? So the word walk, I need to keep a separate embedding for walked and walking and walks and so on. Versus with a character level model, I actually will share the first 4 characters of all of those sequences and only the model needs to know how to process the suffix characters. Even with a subword level model, this is a benefit over a word level tokenization. So yeah, there's 3. There's probably many more. Yeah, go ahead.
The other translation models that we've looked at since F21, do they all use character level coding?
So the question is, do the multilingual and many-to-many translation models use character or byte level encoding? The translation paper we looked at uses sentence piece, which is a subword level tokenization. So it probably has a lot of issues that result with using subword tokenization in this multilingual setting. Obviously, all of these works are very recent, so I think it's a very promising direction to try that many-to-many translation with something like a byte level encoding. You know, it's like competing companies doing this, so it takes some time. But yeah, one of the big drawbacks, though, of these byte and character level encodings is that the sequences are much longer. So we saw in the byte T5 paper, the sequences were like 5 times longer on average than a subword level tokenization. So you know, we're going to talk on Wednesday about efficient transformers that reduce the complexity of the self-attention, theoretically enable these models to operate over long-term dependencies, but still, there's a lot of developments left before these things are feasible for longer texts in practice. All right, so, oh, did I skip a question? I feel like I skipped a question. Yeah, I did. There's this one question.
You can Command Shift T to bring up the last close down.
Oh, really? All right, let me try that. Wow, thank you. This is awesome. How many of you knew that? Oh my God, I'm like a boomer over here. Okay, so this question. Assume we have a training data set for binary sentiment classification that contains only 10 labeled examples. So this is an extremely small training data set. If you see something like this, if you're even confronted with a problem like this in practice, you need to know that training a huge amount of parameters from scratch on this data is never going to work. And the main reason is because of overfitting, right? It's very, very easy to fit these 10 examples using multiple functions, and the vast majority of those are not likely to generalize on your test set or held out data. So that is what you should always be thinking of in these low resource settings. That's why we've spent some time talking about things like prompts, you know, where in the continuous prompt case, you're only learning a very, very small fraction of parameters from scratch on your labeled data set. And this makes them more sample efficient. So because you don't have as much risk of overfitting if you keep most of your parameters frozen. So looking at this question from that lens, there are 2 scenarios here. The first one, you're training a deep recurrent neural network from scratch. Remember, a deep RNN means it has multiple layers. There's a lot of parameters in this network, right? There are those weight matrices at every layer. And even though you're using this pre-trained language model as the input to this RNN, you still have a lot of parameters, especially compared to scenario B, in which you are doing an element-wise average, so there are no parameters associated with the composition, and the only parameters you're training are the classification parameters. So actually, that's probably still too many parameters for this to work, but scenario B is definitely preferable in this case because there are far fewer parameters that you need to train from scratch. All right, so that's done with this question. And finally, the last one. Assume you're given a sequence-to-sequence model trained to solve the task of paraphrase generation. Why might you want to use nucleus sampling versus beam search? This really depends on your use case of paraphrase generation, but there are many use cases where you don't actually want something that is a near identical copy to your input, right? A trivial way in which a model could generate a paraphrase for an input is just to copy the input and return it, right? This is not interesting for us in any use case, but it's perfectly reasonable for the model, right? Assuming its training objective is, you know, produce something that is as close in meaning to the input sentence as possible. And if you use beam search on paraphrase generation, you're going to get near copies of the input sentence that might differ in like a single word, maybe a synonym is flipped here and there. So you might get more semantic preservation, but at the cost of diversity. If you're doing something like data augmentation, where you have, say, like 10 labeled examples like we did in the previous quiz question, we wanted to get more training data without actually labeling more ourselves, we could pass each of those examples to a paraphrase generation model and use the paraphrases to augment our training data. If we do this, our idea is that through the paraphrase process, we're going to inject some sort of diversity into the original training data set. Maybe our paraphrase has a different syntactic structure, or maybe it's using some diverse set of words that were not present in the training data, just giving the model some more signal, the supervised model eventually, to learn from. So in these kinds of settings, we really prefer having a diversity promoting decoding methods such as nucleus sampling instead of something like beam search. All right, any questions about these? Yeah. Oh, you mean, all right, nice. All right, yes, this question?
So when you are doing a low resource training on these type of very huge models, can it happen that the model was learned for the task, or the model was learned? Can it forget data like catastrophic failure?
Yeah, so the question is, if you fine-tune perhaps one of these large models on a small data set, is there a risk that the model will forget all the stuff it learned during pre-training? The answer is yes. That's very possible and happens all the time. So you need to be careful when you're doing fine-tuning that, you know, if your learning rate is too high, for example, or you use the wrong optimizer, you could walk like very far away from the pre-trained model parameters. And in some cases, maybe you don't care about the model's performance on the original pre-training data. If your entire goal is to maximize your performance on the downstream data, then you should only care about, you know, validation performance on the downstream data set. But often, if you start to forget the information encoded in the pre-trained parameters, then you're also going to degrade your performance in the fine-tuning task. So the TA2 posted on Piazza about, you know, general tips and tricks when fine-tuning these models with different data regimes, which you can look into. Yeah.
You said that for back translation and beam search is more often. Could you elaborate on like why that is?
So the question is for back translation, in which we have a machine translation model, we take an input, we go to the target language, then we go the reverse direction to get back to the input. The common approach in existing data sets is to use beam search. Why do we not use sampling? So for back translation, remember we're doing like 2 trips through the translation model. So any noise at either stage is going to, in the first stage, is going to get amplified at the second stage. So the idea is that the noise is injected through like multiple trips through the translation model instead of through the sampling process. And maybe this is a way of getting more controlled noise than you would get through sampling, which obviously has the chance of producing something completely irrelevant. So maybe that's why. Although, you know, most of the back translation data was created before things like nucleus sampling became possible. I think nowadays the models might be so good that even if you do nucleus sampling, you will still get a reasonable translation. Although this is kind of unexplored, so I would be curious to see what happens. But it's probably a combination of sampling methods not being as developed then and wanting to preserve as much meaning as possible. All right, so if there are no further questions, then let's proceed to our, make sure I'm sharing the right thing. Yeah. Okay. So today we're, obviously still continuing with our general theme of large language models, but we're going to look at a new module that allows the language model to retrieve from a huge set of external documents. And so the way I like to explain this is that if you have something like BERT, and if we're looking at BERT's pre-training objective, we might get an instance like Bob went to the mask to get a buzz cut, and we're asking the model to predict what goes in the mask token. And so if you pass this through BERT and then look at the probability distribution, like the output of the softmax layer on top of the mask token, you might see things like barbershop 54%, barber 20%, and so on. And so the model has implicitly encoded all of this knowledge. Like, this is world knowledge, right? If you want to get a haircut, you need to go to some sort of place that cuts hair, right? And these are all places that cut hair. But where is this encoded? This is not encoded explicitly anywhere, right? BERT is not forming any sort of knowledge graph that tells it, oh, haircut occurs in barbershop, right? It is encoding the stuff implicitly somewhere in its parameters, or in a group of parameters distributed across multiple layers. We don't really have methods for isolating where or how this knowledge is stored. All we know is somehow through a huge nonlinear combination of these weights and attention scores and whatever, we're able to get a distribution that resembles something like what we would expect a model that knows this relation in the world to produce. But this is asking a lot of the model, right? For any sort of input with a mask, most of them will require some level of world knowledge, and all of that we're asking the model to stuff somewhere into its parameters. So one of the readings for today was this Realm paper, which makes this argument quite nicely, I think. You know, it's difficult to determine what knowledge is stored in these networks and where. So later in the semester, we'll discuss probe tasks, which allow you at least some window to inspect these models, but they're not always reliable or trustworthy. So there are issues with those. It's not like you can just point to neuron 503 in layer 10 as the haircut neuron, right? That's not how it works. And then the second argument is that the storage space, right, the amount of knowledge that the model encodes is bounded by the size of the network. And this is partially why when we scale up our language models, as we've seen over and over in this class, right, bigger and bigger models are being trained and they work better and better. One possible reason for this is that the models just have more capacity to store all types of knowledge into their parameters implicitly. But this entails that you have to keep expanding the size of your network if you want to add more and more things into it, which is slow and expensive. So some of you might be familiar with the concept of knowledge graphs. Andrew McCallum, a professor here, has done a lot of work on these and inducing them automatically. Basically, they're explicit structured representations of entities and their relations. So like the song Shape of You has all these relations, like sung by Ed Sheeran, who's also the singer of Castle on the Hill. And they're very nice properties when you have such an explicit representation, right? If you know that this relation is singer of, you have the same relation for multiple entities. You can issue queries very easily to your, across your graph, right, to collect whatever you want. However, there are limitations of this approach as well. So it's easy to navigate, of course, but these are very expensive to produce manually, right, at a scale that we want. And so their coverage is always going to be limited. There are methods for automatically inducing these graphs, but they're also limited in the type and scope of the entities and relations that we can have. And very complex relations are hard to encode within this setup, right? So it's easy if it's some sort of like creator of or born in or something like that, but there's a lot of relations that are much less clearly defined, but you still want to encode. So it's hard to collect all of these and put them into such a representation. So another source of knowledge, which is what the Realm paper and other papers in this vein focus on, is unstructured text, right? We have a ton of unstructured text, right? We could imagine the entire Common Crawl or Wikipedia as a source of knowledge. And so here, we if we look at something like GPT-3, it's essentially compressing as much of that knowledge as it can into its parameters, but maybe it just doesn't have enough capacity, even if it is as huge as the models we have now are. So why don't we allow this knowledge to exist outside of the model, like as, maybe a collection of paragraphs from Wikipedia, and allow the model to query this collection instead of forcing it to learn everything from scratch in its parameters. That's the general idea. So we, at this point, have good ways of encoding relatively short pieces of text into representations using something like BERT. So if I have a paragraph from Wikipedia, I could encode it using BERT. So I get a CLS vector, say, representing this paragraph. I can do this for all the paragraphs in Wikipedia. So now I get like millions of these representations. And this forms a data store. Now I have a representation of every paragraph in Wikipedia that's been computed by some model. So now if I have another model that wants to, say, perform language modeling, but it wants access to all of these representations from Wikipedia, it can simply query this data store that we've created instead of learning everything from scratch. So we'll go over this formulation in a couple different methods here. Can we go through quiz 5.2? That's a YouTube question. We'll go over it next week when we talk about the exams. I think next week, yeah. But quiz 5 also involves some of the stuff that we'll talk about today, so that's why I didn't go over it today. Okay, so the realm approach generally works. It has the same objective as BERT, the masked language modeling objective. So if you have something like the mask at the top of the pyramid, and you want to predict what goes into that mask, in BERT, we would just directly pass this thing through our network and look at the softmax probabilities at the mask token to see what the prediction is. Realm has a step before this final softmax prediction. So the first thing we do is we encode this text with the mask token using some sort of model. So here they just use a pre-trained BERT model to encode this text. So you get a vector, like the CLS representation. And then you use that to query your giant data store of all of the Wikipedia paragraphs. So you can imagine you get a vector for this sentence, and you take the dot product of this vector with all of the other vectors in your data store. Or you use some scoring function to find which paragraphs in Wikipedia are most similar to this sentence. So once you do that, you retrieve 1 or k documents from your data store based on these scores. So here we retrieve this document. The pyramidion on top allows for less material higher up on the pyramid. So we've retrieved this paragraph from Wikipedia or sentence from Wikipedia. And now we're just going to concatenate this text along with our input query. So you see we have the mask at the top of the pyramid, a separator token, and then the text of the document that we retrieved. And now we ask our model to predict what goes into the mask token. So this additional step, the intuition is we are giving the model now more context to make this prediction through the retrieval of all possible Wikipedia paragraphs. So if Wikipedia contains something relevant about this mask token, then we would like to retrieve it and feed it into the model. Does that make sense? Yeah.
How would you structure this masking thing if the question is not just a missing word? So what is at the top of the pyramid? That's the question. Then you want to train that model. I think that is the question is going.
Sorry, say that again?
So now your objective is to fill in the mask word.
Right.
What is the question answering problem, right? And what is at the top of the pyramid?
Oh, I see. So yeah, this changes a lot. We'll look at that. So the question is essentially, what happens if instead of masked language modeling, this is like more of a text generation task where we have to, say, produce the answer to a question. We'll look at this at the end of the lecture. There's a work from my own student that I'll discuss in this vein. Yeah.
So I can just add a mask in the end followed by dot. That would be a sentence only. Like, what is the question? What is an answer? What the machine is just a
So the question here is, or comment rather, is can't we just add a mask token at the end of the question to allow the model to fill in the answer? That would work if the answers are always one word long, but in this case, they might be entire paragraphs that you need to generate. So it's not as simple in that case. Yeah. Yeah, so could adding more context degrade the performance? Yeah, so there are a couple of reasons why that could happen. One is the contexts are not relevant, so maybe there was nothing in the data store that helped, and they're actually distracting. Another is that you're making the sequence length longer and longer. Maybe the model starts to struggle with that after some point. So yeah, there are definitely possibilities for that. Yeah, so the question is, isn't this step where we embed the input and then compare it against every single document in our data store, isn't that very expensive? Yes, it is extremely expensive. This model is very slow, but there are tricks to make this go faster using fast nearest neighbors algorithms and so on. We'll talk a little bit more about that in the next few slides. But one of the nice things about this paper is that all of this whole process is trained end to end. So the retrieval is trained end to end, as well as, obviously, we know how the masked language modeling objective is trained. So you're jointly training a retriever and a masked language model. And then you can repurpose both of these as needed for transfer learning if you have a downstream task. So they look at the case of question answering, open domain question answering, like you said, where you only have to produce like one word and you can reuse this whole setup. Yeah. Yeah, so we'll look at another scenario that uses an encoder and decoder, but things start to break down in that case. All right, so in the realm model, so this was like one of the very first approaches to propose this joint retrieval and decoding or prediction type models. Here, if you remember, we are trying to predict this mask token given the context. And in the realm, we're adding this additional step where we're retrieving a document Z. So first, we are retrieving this document Z conditioned on the input text X, so that's this part of the objective here. And then we are going to predict the masked token's identity conditioned on both our input document and the retrieved text. So we're factorizing our probability distribution in this way. This sum means that we are going to use multiple retrievals in order to compute our final probability. They basically take the top k retrievals where it covers like most of the probability mass from the retriever. Okay, so maybe it's not too relevant to go over the exact details of how they implement the encoder, because it's basically just using BERT. They use a pre-trained BERT model, the CLS token of the pre-trained BERT model, to embed both the input and every single one of the Wikipedia articles. And so that's, you see this embed function. Embed input is just a BERT model that you put your input that the mask is on the top of the pyramid into. Embed doc is a similar BERT model that just takes the document from Wikipedia, like a paragraph or sentence from Wikipedia, and passes it through BERT and gets a CLS representation. So you can see their scoring function here, this f of x, the input, and z, which is the document, is just the dot product between these two embeddings. So nothing fancy going on here. The fact that we are training these embedding functions is what is going to cause the scoring function to become meaningful. At least that's the idea. I believe they use separate encoders for both of these things, so like separate BERT models, but I don't remember precisely. So if anyone knows, they can clarify. So right, the embedding function is just BERT, no need to go through the details. Right. The key issue here is that what you described before, that training the retriever is very expensive. The reason for this is that, let's say I have 1 million documents in Wikipedia. Every time I want to score an input against this entire data store, I have to compute these 1 million dot products, right? Of course, I can vectorize this computation, but it's still a very large computation. And so when I compute this probability, if I want to do it exactly, I actually have to sum over every single one of these documents, which is just infeasible. So they use algorithms that are in the class of maximum inner product search. They approximately find the top K scoring articles, these Zs, which much faster than doing it all like linearly as you normally would. So there are some algorithms you can look into that do this. There are a lot of libraries, like FACE is one of them that people commonly use for this. We're not going to go into the exact details of these algorithms here, but this is the main reason why nowadays we can actually do these huge scale retrieval style things. The lookups are not that slow anymore, although they're still slow. Like, this is not a fast thing to do by any means. So what this requires is that you pre-compute these BERT embeddings of all the documents, and you build an index over them. And this operation is very expensive. So one thing that they do in this paper is that they only refresh this index every few hundred training steps, which means that sometimes the BERT embeddings for the documents are stale in that you have updated your input encoder several times, but you haven't performed these updates on your document encoding model. That's because it's just too expensive to do this at every time step and rebuild the index. And so they have this figure in their paper where they detail this process. Like, you have to specify some number of updates where you don't update the document embeddings from Wikipedia. So they become stale, but then at some point you do re-update them and you continue training like this. So this asynchronous update of the retriever encoder and the rest of the model is what allows them to train, and it seems to be okay even if some of the document representations get stale. The model still seems to train pretty well, which is nice. Yeah, so this is probably the first approach to try incorporating this large-scale retrieval into something like BERT's masked language modeling objective. Any questions? Yeah.
So the question of the source, which is used for building that index, so is it Wikipedia or
Yeah, the source of the retrieval data store in this case is Wikipedia. So is your question, is it live data, meaning if Wikipedia is updated, this is also updated?
Yeah.
No, so all of these kinds of papers will use a dump of Wikipedia from some month, but they're not updated live. Yeah.
I think for that question, there was a figure at the end of the paper where they show using like a 2018 or something Wikipedia, and they do updated with 2020 dump, and it's still able to like find, do the same thing that's been updated.
Yeah, so that is actually a big advantage of these kinds of models, is that, I should have mentioned this earlier, is that so you can train the model with one data store, and you can swap out the data store at test time, because the model has learned how to use the documents in the training data store. If you have a new document, you can just add it to your existing data store at test time, provided your embedding function knows how to produce a good representation of this new document. But this is much cheaper than having to retrain your model every time you get a new document that you want to add into its parameters. So that's another huge advantage of these kinds of models. All right. Oh, there's a, would we benefit in Realm if we add a filter method, maybe use TF-IDF scores of the query score to input documents before the end-to-end training? Oh, I assume this is an approach to make the nearest neighbors faster. Probably. I think you might lose some important documents doing this filtering where maybe there's not a lot of string match, but they're still important. I don't know. It would be interesting to try. Maybe they tried in their paper. I forgot. All right, so there are some other tricks in Realm that I wanted to highlight because at least the first one has been tried many times before in other work as well. And it's, what kind of span are you going to mask if you have to select a span of text to mask? So Realm is masking spans, not just individual words. By masking a span, I mean it just turns contiguous sequences of subwords into mask tokens. So in Realm, they choose explicitly to mask out texts that correspond to entities and dates. Why do you think they would do that in this particular setup? Yeah, so entities and dates are likely to, occur in Wikipedia, right? There are lots of Wikipedia articles about people and places and things. There are not Wikipedia articles, I think, about like random verbs. So if you mask out a random verb, then it's going to be kind of hard to benefit from the retrieval. So dates and names and things like that, obvious places where you can benefit from having this external knowledge from a source like Wikipedia. Yeah. So the question is, if this model is focused on things like names and dates, and at test time, if you want to add a new article about some new person that wasn't there before during training, isn't this kind of hard because the model has to learn to deal with this new entity that it's not seen before? That's certainly true. It is hard, and it's way harder for a pre-trained model that's never seen this article or name before in its training data ever, versus a model like this one, where the model essentially needs to learn a similarity function, right? So if it gets an input with a mask that's about this new article that it hasn't seen in pre-training, it has to be able to retrieve the new article from the data store and then somehow use it to produce the missing token, right? So the similarity function, if it's learned it on other data and it still seems to work for this new article, then this is a clear advantage for this kind of model. So it kind of depends on the power of your similarity score, but if you've trained this function on all of Wikipedia with a large enough language model, it turns out to be quite good. Okay. As I mentioned, this Realm paper, yeah. Oh, my bad. Right, so they also add this null document to so they retrieve the top K documents, top K scoring documents. They also add a null document which is completely empty. And this is because they claim that they don't want the model to learn to always rely on the retrieved text. They wanted to also encode some knowledge in its implicitly in its parameters. I suspect this would happen anyway, but I'm not sure if they ablate this and see if it actually makes a difference or not. But it has some intuition, right? They want the model to learn to not always just ignore its own prediction, but rather rely both on the retrieved text as well as whatever it's encoded in its knowledge. Okay, so the evaluation of this model is on open domain question answering. So it's very similar to Squad, like the types of questions that are asked and the types of answers, except you don't get the passage that the answer exists in beforehand. So you just get a question, you have to answer it, you have to produce an answer. So this is much harder than the Squad problem because you can essentially boil it down to first retrieve a relevant document and then perform a Squad style task of extracting the answer span from that document. But there's a two-stage process. First you retrieve, then you extract. So you can see how this setup is conducive to this Realm style approach. because realm also first retrieves and then predicts. Okay, so they evaluate this, I think, on natural questions. That's their main evaluation, which is a data set released by Google for this task. Basically, you can see compared to the baseline of BERT, which was getting 26.5, I think this is F1 score, their realm models are doing much, much better on this task. So this is a clear sign that encoding all of this knowledge into BERT's parameters alone is not an effective way of handling an open domain problem involving retrieval. Actually having an explicit retriever makes a big difference here. And I think things have improved since then. So this was one of their evaluations. And here is one qualitative example so you can see how it's actually improving. Here the input is an equilateral triangle is easily constructed using a straight edge and a compass because 3 is a blank prime. So here the model is asked to fill in what is missing. And if you just pass this thing through BERT, the correct word here is format, whatever. And its probability is very low with no retrieval. But if you use realm, the probability with a particular document concatenated to this input is 100%. So there is some document where if you add it to the input, the model knows, like, it's very certain what the answer is. However, remember that we don't just add one document, right? In realm, we're concatenating like multiple documents, K documents. Here, if they marginalize, so they sum over the 8 documents that is retrieved by realm, they get a lower probability, but still much, much higher than what BERT produced. So you can see clearly that retrieving some of these documents has a big impact on predicting the right answer. Yeah. So the question is, do we have any constraint at all on the output space of this model? No. So this model is comparable to BERT in that when it's producing this answer for Mont, this is 3 BERT word pieces. So it has to produce these subwords that correspond to this answer out of the entire vocabulary of BERT. So no constraints on the output space at all. You could do much better if you constrain the answer space, but that's less interesting, right? Okay. So the next, I see a question. How does this compare with open retrieval conversational QA, where we also have a learned retriever, re-ranker, reader? So the main difference between these two settings is that obviously in conversational QA, you have a sequence of questions that are being asked, like, what is an equilateral triangle? How is it constructed? What are other types of triangles, right? You have a sequence of related questions, and the model's prediction at any one time step depends not only on the retrieved documents and the current question, but also the history of this dialogue, like all the other previous questions, answers, the retrieved documents for all the other previous questions and answers. There's essentially, the task just requires an extra layer of conditioning over the previous history of the interaction. So that's the main difference. All right, but we're going to talk about machine translation now, because recent work has tried to apply the same sort of retrieval style modeling to things like language modeling and machine translation in a slightly different way, but still interesting. So I'll just explain this through the diagram in this paper. Also, the author of this paper is coming, I think in January, coming like virtually to give a talk here. So if you're interested in this work, you should check that out as part of the IR talk seminar thing. So here in machine translation, imagine that we are partially through the decoding process. We have this input, which I will not produce, I will not pronounce. And then our decoder has generated 2 tokens, I have. And we're interested in knowing what the next word is, obviously. So if I had a normal machine translation model, I would just feed I have into the decoder, let it do its attention and its cross attention over this input, and then look at the probability distribution in the softmax and see what the next word should be based on that, doing a beam search or a greedy search or whatever. So that's the traditional way. But in this method, there's a retrieval step before you do that. So similar to realm. So here, this representation is the decoder's representation of this prefix I have. So the representation at the word have, right before you would feed this into the softmax layer to predict the next word. So that's this vector here. And so the idea is that in machine translation, I have a lot of training data, like these parallel training data pairs. So why don't I just use my entire training data set as a retrieval corpus? Which is kind of strange if you first think about it. But in the training data set, so this input here is a test input. We've never seen it before. The idea is that even if we've never seen it before, there are probably a lot of similar sentences in the training data, and retrieving those sentences and seeing the ground truth word that follows the corresponding part of that sentence that corresponds to this will be helpful in determining what word should come next. So not just relying on our model's prediction, but also the statistics of the training data. So my training data consists of a bunch of different sentences, and there are prefixes here like I have, I had, I enjoy, I have, and so on, that are very similar to the thing that I've already generated. So if I cache every single hidden state in my training data set, and that's actually what this method does, which is kind of crazy, because you imagine one sentence in machine translation, right? And we're talking about the decoder's states here. So and this is French to English, so the decoder is processing English sentences. Every sentence has, n hidden states corresponding to the n words in that English sentence, right? So if I have 100 sentences in my training data, I'm going to have 100 n times, the length of each of those sentence hidden states. And generally, we have like million training data sentences. So I'm caching a lot of vectors in this kind of setting. For every single prefix of the English output, I have a different vector. That is the output of my transformer at that time. All of these are cached. And now I do the exact same thing as I did in Realm. I have my query vector, which comes from the current decoder's representation. And my keys are just all of these hidden states that I've cached from my training data. I can apply fast inner products search, and I can get the top K scoring hidden states from my training data set. Then those are the ones that are shown here. So I have additional information here compared to Realm. In this case, I also know the ground truth word that followed every single one of these contexts that I've retrieved, right? Because they're just training data set. I know what the next word is in all of these cases. So in this case, I retrieved this I have, the next word was been. Here I had been, I enjoy summer, maybe this one's less relevant, I have my, and so on. So I've retrieved some number of things, and I can look at what the ground truth next word is for all of these things. So intuitively, I can take some statistics that come from the ground truth next words, and I can interpolate this distribution with the model's own predicted distribution in order to get my final distribution of what the next word is. That's the high-level approach. So let's see how that plays out. Here, I'm going to look at the score of my representation with each of these key vectors. So this, could be just a simple dot product, for instance. So I get that this I have been had a distance of 4. I enjoy summer, not very relevant, had a distance of 100. So maybe we don't want to use this one as much. So after we compute these distances, and this is just for intuition, right? We're going to take the the bottom k, the closest representations to my current query, this one, and we're going to look at their distances. We're basically just going to normalize those distances into a distribution. So we get, you know, I have this first one is now the most similar of my training set to to my query vector. So I have after normalization, gets 40% of the probability. The two next similar things are I have been and, I had been and I have been. So both of these are, the next word is been. So after normalization will aggregate because it's the same next word. So my final distribution is 40% over my and 60% over been. So this is what happens after the retrieval stage. So now I have one distribution for the next word. Note that this doesn't depend on the model's own softmax layer at all, right? We computed this distribution purely using the statistics of the next word from all the examples that we retrieved. So this is what we call the final KNN distribution, K nearest neighbors distribution. But we still have to do this interpolation with the model's own prediction of what comes next. So this is very straightforward. They basically have some hyperparameter here where they will just weight, this is something they choose beforehand. They'll weight the KNN distribution by some percentage and the decoder's predicted distribution with 1 minus that percentage, right? So very standard. You can learn this value, which they don't do in their paper, and get maybe slightly better results, but you could even learn this value for every position in the sequence that you're at. There's a lot more work that can be done here, but the results of this simple approach are already very strong. Also before I get to the results, I should mention that this doesn't actually require any training, right? Here, we took an existing neural machine translation system. We used it to produce the vectors for our data store. And at test time, we are just simply taking the representation that the decoder produces and using it to query all these keys that our MT system already created. So there's literally no training involved. This is purely just augmenting an existing neural machine translation system with a retrieval module. Yeah. So the question is, how do you get all of these intermediate hidden states to put in your data store? They train their machine translation model themselves, so they have access to all of the model outputs. In general, if you're using a model where you can't get access to this, that's pretty suspicious, and there should be a way somehow, but that whatever framework it is hiding a lot of useful information from you if that's the case. In general, it should be like obviously in GPT-3 you don't get any access to the model representations, but that's a kind of rare case. With any Hugging Face model, it should be trivial to get access to this kind of thing. Yeah, so you can apply this to any pre-trained sequence-to-sequence model. It's a pretty interesting approach. However, it is very expensive, so that's the drawback. Here, you have a key store of billions of items because your data store includes every hidden state in the training data set, which is insane. And if they're retrieving the top 64 scoring keys at every time step. And they say that this slows down their generation speed at test time more than 2 orders of magnitude compared to the base neural machine translation system, which is already probably pretty slow. So this is not feasible to implement if you're in a production environment where your latency actually matters a lot. Like Google Translate, this would be probably require a ton of compute if they wanted to integrate this into their translation systems. So one research direction now is trying to make this faster. How can you make it faster, and so on. But the advantage is if you manage to do this, you're going to get slightly higher quality translations. They look at this across many different language pairs. German to English, maybe a 1-point blue improvement, Russian to English, and so on. So here, English to German, they get almost 3 blue points. And remember, we said that anything over 1 blue score is a pretty significant improvement. But you can also see the data store sizes here, right? It's like 6.5 billion entries in this English to German case. So kind of huge, making it very slow. One easy way to make the model faster is to just use a smaller data store. So maybe instead of caching every single hidden state in your training data set, maybe you cache only a fraction of the hidden states, and maybe you have some intelligent method of choosing which things to cache. However, if you do this, you also decrease the advantage, the improvement that you get from using this kind of method. So there are always trade-offs. Yeah.
Why is it just the final iterating?
Yeah, so the question is, what do I mean by cache the hidden state? Yeah, when I say hidden state, I mean the final token level representation in the decoder, the final layer, yeah. I mean, that's another, like if you want to go all the way, you could cache every single layers, and then get billions, tens of hundreds of billions of things, but it's hard to see how this is going to improve much further, yeah. Yeah. Introducing a what? A copying mechanism. Yes. So the question is, what is the relationship between this and a copy mechanism? It's very similar in that in a copy mechanism, this term here would come from like the model's input. It would just maybe upweight all of the things that it saw in its input or something like that. Here, this is coming from the output of a retriever. So, but this general idea of interpolating some distribution that comes from outside the model, so that would be like the copied probabilities in a copy mechanism with the model's own predicted probabilities is similar in theory. So yeah. All right, other questions? Yeah.
Couldn't it be kind of degenerate, like if you have a lot of examples where one word that follows is very common, but then in the context of the word you're actually trying to translate is something very specific, like a named entity, wouldn't it give a lot of, like, it would just prefer to do the things way more likely in the example versus what it actually wants to produce?
Yeah, so the question is, couldn't this retrieval model actually cause the model to go wrong in some cases where its predicted probability is correct, but the retrieval, maybe there's some common next word that doesn't actually apply in this case. That's definitely true. That could happen and probably does happen in some cases. Like we have seen, one of my students has been working on this kind of thing, and if you change these lambdas in such a way that maybe you increase it to favor the retrieval distribution, your performance degrades significantly. And there's definitely a sweet spot where you have to tune these things to get a benefit from the retrieval. So relying too heavily on it, it does degrade your performance, yeah. Okay, so another thing that is, well, actually, I'll just move on for the sake of time. I think I'm done with this. Yeah, so in the last part of this, last 10 minutes, I wanted to talk about extending these ideas of retrieval to an actual generation problem. So far, we saw one way in this machine translation thing where you retrieve at every single time step, and you're retrieving essentially the next word. But this doesn't really make sense outside of the context of machine translation, right? There's not many other tasks where you can just get the statistics of the next word from a large training data set and that'll be relevant to the task you're solving. Certainly in something like long form question answering, it's not really a viable method. So I'll just briefly just explain this task, which is also the one in your quiz 5. I forgot to cover this lecture before I assigned the quiz, so probably some of you were confused with how to build a model, but I mean, you can still build a model without a retrieval component. So I'm sure many of you hopefully looked at this subreddit and saw the format of the questions and answers, but the answers are generally multiple paragraphs long, right? So this is not the case where your answers can just be reformulated into a one or few subword prediction from BERT or something like that. So this task, similar to the open domain QA task we described before, involves both retrieval and prediction, except here the prediction is generating multiple paragraphs. So if you have this question, you need to retrieve, several possibly relevant documents that will help answer this question, and then put this into a model to generate the answer. So the way in which we did this, so my student Kalpesh was the lead on this, was you take a large language model. One way to solve this QA problem is just put the question into the language model as a prefix and then see what the model generates as output. Obviously, this approach does not use any information from like retrieved articles. So another approach is take your large language model, then encode the question, and use your query representation of that question to retrieve a bunch of documents. And then, similar to Realm, just concatenate the text of those articles with the original question. So here, why do humans need to eat many kinds of foods to get their vitamins, but cows only need grass to survive? I would take this question, I would add a separator token after this, I would add the text of this article on ruminant, I would add the text of this article on human digestive system, and then I would ask the model to produce the answer. So the retrieval, just like in Realm, is only impacting the input text that gets fed into the model. So like the idea is that the answers in this data set generally require you to have some form of knowledge, domain specific knowledge. Like to answer this question, if you didn't already know it, you would probably have to look up these relevant articles to be able to write the answer, right? So this is the process that we're modeling, yeah. So the question is, doesn't the ELI5 dataset give you the articles that you need? So the ELI5 dataset gives you the ground truth articles that you should retrieve only for a small portion of the held out data, like the validation set and the test set, where they manually annotated, like based on this question, you should retrieve this article, and so on. But it's very unclear if a model actually needs to retrieve or not. And that is basically what I wanted to highlight with this work, is that in this kind of generation task, the model has been pre-trained on a huge amount of data, like say GPT-3, right? It's seen billions of words. We don't know what it's already encoded implicitly into its parameters versus what it was unable to encode. And so if you get a question like this, you don't actually know if the model needs to retrieve anything in order to answer it or not. Perhaps it's already seen many documents about cow digestive systems, and it has no need to retrieve a Wikipedia article to improve its generation quality. There are a lot of things that make this kind of thing pretty complicated. But going back to this data set, there's a leaderboard for it on this KILT website, where you evaluate both the retrieval quality based on these ground truth annotations, as well as the generation quality. And here, they're using the Rouge score to evaluate the generation quality. So remember that Rouge is a recall-based metric, right? So the model generates some answer, and we have ground truth answers that Reddit users wrote on the ELI5 data set. And Rouge is basically saying how much of that ground truth answer also occurs in the generated text, right? But this is not a great metric, right? Rouge is word and n-gram based metric, you can imagine here there could be several different answers. And one natural question is, what is a rouge score between human answers of the multiple human answers of the same question? So we built this model, and it was, really getting state-of-the-art rouge score. Then we looked at the outputs, and they were not very good. And we looked at the retrievals, and the model seemed to not even be using the retrievals. So one experiment we did was, so we trained the model with the retrievals, and then at test time, we evaluated the model in two scenarios. One where it used its predicted retrievals, and another where we replaced the predicted retrievals with completely random documents. And you can see the rouge difference here. The predicted retrieval is like 0.2 rouge better than completely random documents, which is not, very confidence building in our method. There are even weirder results. So we ask humans, here's an output from a model trained with random retrievals versus trained with the predicted retrievals. Choose which of the two answers you like better. They seem to prefer having random retrieval answers, and obviously that's it's definitely even worse. And then between the prediction and the gold answer, they preferred the gold answer, the human written answer, almost 72% of the time. So the humans were able to spot the difference between a gold human written answer and a model generated answer, but they could not spot the difference between a model using real predicted retrievals versus random documents. So a long way to go before retrieval is beneficial to these more open-ended text generation problems. Finally, if you're interested in this data set, there are a couple different issues which you should be aware of. Also, if you're creating a data set for your project, there are some things that are here that could also be affecting your data set. So one is, remember that we want our held out examples to be unique, right? They shouldn't be things that occur in the training set. And so in this data set, based on, there's only so many questions that people ask on this subreddit. They ask them in many different ways. So here in the validation set, can you protect electronics from EMPs, solar flares? We looked at the most similar training set questions. You can see there's several very similar questions that are not identical in terms of string match or anything like that, but a paraphrase model could perhaps detect them. And this is really hampering the utility of our retrieval as well, because if you have a model that's fine-tuned on this training data set of ELI5, and at test time you get a question that's like a paraphrase of a training question, why would you need to retrieve a document when you already know the answer because it was in your training set, right? So a lot of potential confounds to training a reasonable retriever in this way. And so like 81% of the held out questions in this data set have some sort of paraphrase or near identical question in the training set. So this is a huge issue when training a retriever. Another issue, going back to our lecture from before, is the evaluation metric. So we're using rouge. We found that even retrieving completely random answers to other questions gets you a pretty high rouge, sometimes even higher rouge than the gold answer. So here, I think this is still about the electronics question. This random training answer, the fast lane, slow lane, this has nothing to do with the EMPs or electronics, but word overlap, right? That's all rouge is, and it gives you a 19.5.4 rouge compared to the gold answer, which is getting 18.6. So how can you have confidence in this metric when your gold answers aren't even being scored higher than random answers? And one other thing is evaluation. So if rouge isn't a good way to evaluate, what is? And one way you could think about doing this is, well, maybe I can ask humans which answer is more correct. But in this data set, that's very difficult because you need expert knowledge in order to assess the correctness of a particular answer. So this is a very hard problem. It's exciting, right? Because this is kind of like synthesizing every QA task into one task where you can solve squad-like questions, open domain questions, and these more long-form questions all within one model. But it's also much harder to evaluate, hard to train models on, hard to even collect data sets for. So yeah, I'll just end with a generated example from our model. Why are almost all boats white? And it starts off pretty reasonable. They're painted white for obvious reasons. Okay, maybe not reasonable, as they are. I think most boats are not inexpensive. But it's, you know, it's giving you some reasons that seem, although kind of irrelevant. Then you get some Reddit artifacts. There are many, many more reasons for why ships are white, but those are the ones I know of. I'm sure there are many reasons, but those are the ones I know of. Edit, I forgot to mention that. So, you know, another issue with the source of the data, right? The model is going to pick up on all of these kinds of weird behaviors from Reddit users and so on. So anyway, next time we'll talk about efficient transformers, so see you then.